Hi guys, welcome back to Data Every Day. Today we'll be looking at a dataset of Pokémon with stats. Essentially we're going to be trying to predict whether a Pokémon is legendary or not based on a series of stats that have been gathered from these three websites. So you can see a bunch of stats. Alberto, put together this nice dataset from a collection of these three to give us what we are going to use to try to predict the legendary status of a Pokemon. So let's hop in. I have the task for today, which is given data about various Pokemon. Let's try to predict if a given Pokemon is legendary or not. And we'll be using a TensorFlow artificial neural network to make our predictions. So I have the libraries we'll be using today ready to import. It will be NumPy, Pandas, Matplotlib, pretty standard. Seaborn for data visualization, Plotly Express also for data visualization, and for pre-processing we'll use label encoder and standard scaler from sklearn, along with the train test split function. For training we'll use TensorFlow as I stated above, and for some post-training analysis we'll be using PCA from sklearn. So I'm going to import those, and then let's load in our data using the pandas.readcsv function. You can get the file path right over here, copy that, paste it in, and we'll take a look. So before I move on, I just want to make a copy of it. We'll call it data raw equals data.copy, so I can get the cleaned, the unprocessed version of the dataset later on when I'm doing analysis. And we can look at this data set and notice a few things. One, there are a few columns we don't need here, namely the number column and the name column. Two, there is at least one null value in this data set. And three, everything else is numerical except for the one we're trying to predict, which is legendary. And that's just Boolean, so it'll be easy to convert. So let's start pre-processing. Actually, we'll do cleaning. And let's just take a look at some of the preliminary info, just confirming what we saw before. And it looks like there's only one column with null values. There's three object columns, so non-numeric, and a Boolean column, which is also, you could think of as non-numeric, but it's very simple to turn into numeric. This is sort of redundant, but I just want to make sure, double check, get a good sense of how many null values we have here. And it looks like there's only one column with null values, which is type 2. And if we look up here, there's only 800 rows, right? If we have a column that has nearly 400, so that's nearly 50% null, it's not really worth keeping that column, right? Because if we tried imputing the values with something, we'd end up, we wouldn't have enough data to gate the mean for those values. Half the values we fill with the mean. So we're just going to drop it. Data.drop type 2. And while I'm doing this, I might as well drop those unnecessary columns that we saw before, which were number and name. Number, since it's redundant. I mean, we could use this as the index. There's no problem with that, but it doesn't really matter. We're just going to drop it, and we're going to drop name as well, because this will not help us in recognizing if a Pokemon is legendary or not. So number, name, and type 2. And we're dropping from the axis 1, column axis, and we'll just set data equal to that. So now I'd like to do a bit of EDA, exploratory data analysis. And actually, one more thing before that, I'm just going to turn the legendary column into ones and zeros instead of true and false. So very easy to do that is, it's very easy to convert. We just do data.sublegendary.asType numpy.int. And that will just convert it to zeros and ones. Whoops. So we'll just set that equal. And now let's take one more look at our data. Okay, so this is good. Now I want to check the unique values of this type 1 column. Since this is our only categorical variable, we want to see what kind of values does it take on. And I have some idea, but I just want to see them all. So data subtype 1 dot unique. And it looks like we have a number of nominal, it's a nominal feature with a number of categories. So for this, we'll definitely use one-hot encoding, right? There's no order between these, just completely, we'll make a dummy matrix out of the columns. Out of this column, we'll make dummy columns, and then we'll append that on to our data set to get the one-hot version. And we have numeric columns, which I'm just going to store in a variable so we can reference it easily. Numeric columns is going to be data.drop type 1 dot columns. So this here is the data set. Oh, right, that makes sense. This here is the data set without type 1, and if we get the columns of that, it's just going to be the list of columns without type 1. I could have constructed that manually, but why do that? So numeric columns is going to be all of the column names except type 1, so these. And then we're just going to get a correlation matrix for those numeric columns. And we're doing this so we can see a nice heat map of the correlations between the variables. So correlation matrix equals data subnumeric columns dot core. That's a pandas function that allows us to just generate the correlation matrix. And with that, we can then create a new figure. Let's give it a fig size of 18 by 15. And we will use the seaborn heat map function here to generate a heat map from our correlation matrix. I'm just going to turn on annotations so we can see the actual correlation values. I'm going to also specify the bounds of the correlation values. And then I'm just going to do plt.show. And here it is. So you can notice a few things. One, we have this this variable total, which is actually just a sum of all the other features, right? So it makes sense that we have high correlation values between total and all the other values that are its components. Aside from total, it doesn't look like we have very many strong correlations. The most we seem to get is around 0.5. And nothing negative. It's very interesting. So the one we're also interested in is the legendary column. This is what we're trying to predict. And we'll notice that there is no one feature that is like outstandingly correlated with legendary, right? The most we have is 0.5, and that's with total. So we're going to hope that a combination of all of these features will be enough to predict whether a Pokemon is legendary or not with high accuracy. And with that, I'm just going to do one more visualization, which will just be, let's just to see a distribution of each of the variables, each of the columns. So for that, I'm going to use a kernel density estimate plot, which is basically a continuous approximation of the histogram for a given column. So plot.figure, here we'll make it a fig size of let's make 25 by 10. I want it very wide here. Actually, that might be a little much. Let's do like 18 by 18 by 5. Let's try. Yeah, 18 by 10. Why not? We can always adjust. And then for each column in, And now there might be some issues, because if we're going to plot all of our distributions on the same scale, we have to make sure that the values that these take are on the same scale, right? So if we plot legendary in with the rest of it, we're going to have that distribution is all the way on one side because it can only take a 1 or a 0, and all the rest is going to be somewhere else, right? So I'll show you what I mean. I'll actually just do all of them here. So I'll do column and numeric columns. So for every numeric column, we're going to generate a KDE plot, kernel density estimate plot, of that particular column, and we're going to turn on shading, so it's just going to give it a nice little effect there. And plt.show. So we get an error. What's the problem? Oh yeah, no, but we still see the plot a little. So you can see what I'm talking about. Why is it like this? Anyway, you see there's this really tight distribution and this really long distribution for let me get, wow, I can't see it all at once. Okay, let me try changing the figure size here. I'll do what I had before, and that's not working either. So let's just try making it small. 10 by, I'll make it 5 by 10. Okay, this does it. So you can see we have this really tight distribution and this really long distribution. That's for generation and for total, right? But these are the ones we're really interested in. So I'm not going to include generation and total in these columns. So instead of numeric columns here, I'm just going to, I could type them in. Could also just grab them from up here. So just these ones are the ones I want. So column in new list of this, and I just have to go in and make these into elements like this. Alright. And now we can see the plot better, and let me actually change the size again. So actually 20 by 10. Okay. So here is distributions of each of the variables: HP, attack, defense, special attack, special defense, and speed. We notice they're all centered around a very similar mean, which is, I don't know, something like 60 or something. And so they occur in high frequency around 60. They go up to values as high as 250. Some of them taper off before that, and very few are below 0. Although we do have some below 0. Actually, we probably don't. Right. So this is a continuous approximation of the histogram. So even though it looks like we might have some stuff down here, we might not. Right. If the highest point is here on the histogram, you can imagine there's a bar here. It brings it down this continuous approximation, which will still make it appear that there's something less than 0. But my guess is it goes from 0 to something around 250 something. And so this is just to get a better sense of what the data looks like. Now they take on a similar range, but I'm still going to scale all the features just so that we have as similar range as possible. And with that, we will start pre-processing. So getting it ready to train. Let's look at the data types. And again, we only have this one object that we're going to have to encode with one-hot encoding. Encoding. Let's just make a one-hot encoding function that we'll call it one-hot encode. And it'll take in a data frame, a column, and a prefix. And we could implement this with the multi-column feature, but since we're only encoding one column here, I'm just going to write it with a single column. And that's just going to be, we'll start off by making a copy of the data frame, then constructing a dummies matrix which we'll use pandas.getDummies, data subcolumn, not data, sorry, df subcolumn, and then we'll append the prefix that we specify in the parameter, and that will give it just a little prefix. It'll append onto the beginning of the string for the column names in the dummies matrix. Then we will concatenate the original data frame and the dummies data frame together along the column axis, and then we will drop the original column from the column axis. So we drop it because we've now encoded it into dummies, so we no longer need the original one. And then we will return the data frame when we're done. Alright, so if I one-hot encode the data, and the column I'm going to be encoding is type 1, and we'll give it a prefix of t, then that looks like this. The original type 1 column is gone, and has been replaced with all these. A new column for each unique value in the original type 1, and a 1 corresponds to the original column having that value. So with this, we realize our entire dataset is in numerical form, and I'm just going to store that in data now. And I'll just keep it on the screen so we can see. Now we can split and scale the data. Alright, so splitting. We're going to create a target column and feature columns. Feature data frame, feature array, however you want to call it. So Y is going to be our target column, which will be data sub legendary. That's what we're trying to predict. And X is going to be everything except the target column. Alright. So Y looks like this, X looks like this, right? There's no legendary in this one. And we're going to scale X. So a scalar is going to be a new standard scalar object. This is imported from sklearn. And X is going to be scalar.fitTransformX. So we're just scaling it. And standard scalar gives all the columns mean 0 and variance 1. So let's run that. And then we'll split it further into train and test sets. So xtrain xtest, ytrain ytest. It's going to be train test split x y, and we'll give it a train size of 70%, 0.7. And let's also include a random state so we can reproduce the effects. We'll give it 42. It's the number I like to use. And with that, we should be ready to train. So training. We're going to construct a very simple TensorFlow 2 hidden layer neural network. Let's take a look at the shape of our features. We have 26 features. So we'll start by making an input layer, which will be tf.keras.input, and give it a shape of 26. So it's a vector of length 26. Then our next layer, this will be our first hidden layer, will be tf.keras.layers.dense. So a dense or fully connected layer. And we'll use 64 activations, and we'll give it an activation function of ReLU. And we'll pass in inputs. Then we'll give it another identical layer, also hidden, also fully connected, and here we'll pass in X. Then for outputs, we'll have one more dense layer, except a single activation representing the probability estimate of the positive label. So how probable is it that this Pokemon is legendary? That's going to be that one activation, and that will have a sigmoid activation. So it will take a value between 0 and 1. And we're passing an X here. Then we'll construct our model, which will just be tf.keras.model, taking in the inputs that we created and the outputs that we created. And then we can compile our model. Let's give it an atom optimizer. we'll use binary cross entropy as the loss function. And for the metrics, if you look at the data set, notice, okay, here, 91% of them are not legendary. So that leaves almost 9%, no, 8% of the Pokemon are legendary. And so what that means is if we use accuracy as our metric, it's not going to tell us much about how well we're doing. Because, so if let's say we guessed that all the Pokemon were not legendary, we'd then have a 91.9% accuracy, right? Because the only ones we get wrong are the legendary Pokemon, and because there's so few of them, it's not really affecting our accuracy too much. So instead, well, we can use accuracy, but we also should include a better metric. How about the area under the curve of the receiver operating characteristic curve, tf.keras.metrics.auc. And this is going to give us a metric that it is affected by performance across different classification thresholds, and it's affected by performance within each class. So it's much better at telling us about how our model is performing than accuracy is in this case. If we were dealing with a 50-50 split between legendary and non-legendary Pokemon, then accuracy would be a perfectly fine metric. But it still might be useful to include this as well. Because let's say one of those classes we were classifying more accurately than the other, then yeah, this would tell us more about that. Alright, so we compile our model, and then we're going to declare a batch size, 32, and number of epochs. We can start with 100. Then we're going to store our model's fit history in a variable called history, and fit our model to the training set, xtrain and ytrain. Then we'll give it a validation split. 20% of the data will be used for cross-validation. And then we will specify the batch size as we did before, and same with the epochs. Alright, and let's run it. Let's train it, and it should be metrics. Alright, that's looking promising right there, but let's plot it, and I'll use Plotly here. So px is Plotly Express. .line, give us a line chart. We're going to draw our data from history.history, and we're going to plot the loss and val loss arrays. So y is going to be the things we're plotting on the y-axis, and they come from history.history. And for labels, we'll make the x-axis epoch and the y-axis loss, and we'll give it a title. Just make it a loss over time. Alright, let's call that fig loss, and we'll do fig loss.show. And here it is. Over the number of epochs, our training loss continues to decrease as it gets better and better at learning. However, at some point, it starts to memorize the training set and fails to perform on the validation set, which is new unseen data. And then you can see the validation loss starts to go back up. So we have to find the minimum of the validation loss. So we can find that with numpy.argmin val loss. Actually, it's history.history sub val loss. And it's epoch 16. So right here is the minimum. And before I actually retrain the model, I'm just going to make a similar plot using the AUC curve. So this will be fig AUC. We'll use AUC and val AUC as our data. The y-axis will say AUC, and the title will be AUC over time. And we'll plot it. And very similar thing. Some interesting stuff is going on over here. As it starts to overfit, you can see that the AUC starts to go down again. Now, I assume this is the difference between a single misclassified example. That's why it's so jagged. But basically, I'm going to try something. First, I'm going to retrain it for 16 epochs, which looks like a very promising value. So 16, retrain it. Then I'll take another look. And now you can see they're converging, not going back up anymore. This is called early stopping. And we're going to evaluate the model on the test set to see how well it's doing on a fresh, brand new set of data. And 97.27 AUC. That's pretty good. That's really good. That means it's doing a very good job at classifying non-legendary Pokemon, but it's also doing a very good job at classifying legendary Pokemon. So I'm going to try something else, which is I'm going to try adding a callback function here. And it's going to be reduce learning rate on plateau. And basically this is going to, every time it sees that the loss starts to plateau, or it starts to decrease at an ever decreasing rate, it's going to lower the training, lower the learning rate, so that we can converge more nicely into whatever minimum it's trying to get into. However, this is at the expense of possibly converging to a local minimum. So I'm going to try it though, and I'm going to train it for a long time because this is much less prone to overfitting when we use this callback function. And you can see it is completely converged, unchanging. But let's see how and we'll check this one too. See, completely converged. But we'll run this, and we actually, is that less? I think it said 9727 before. Let's try training it for, let's see, what's the minimum here? 20. I'm going to try training for 20 epochs. And let's see how that goes. 97.3. Okay, this is the best we've gotten so far. So let's just stop it here. Alright, this is very good. Yeah, it looks pretty decent. I think, let's see. So actually I should have put results up here. I'm going to do some post-training analysis. And I want to see what's causing this. Which examples are being misclassified? Because so it's 95% accurate, which means there are 5%, a little less than 5% of the data is being inaccurately classified. So I'm going to create. I want to make a list of indices of the original dataset that is misclassifying, so that we can get a sense of what kind of data that is. So I'm going to do model.predict xtest. So this is going to generate predictions for the test set. So it will have the same accuracy as this, right? But these will be the actual predictions, not just a score. Looks like this. So these are probability estimates, and I'm going to check if a given estimate is greater than 0.5, and now we have the true-false values. Now if I sum across this, I'll get 20. And this is just to confirm that we're getting the same data here, the same information, and that 0.5 is our classification threshold. We'll do, okay, so length of y test is 240. 240 minus 20 is going to give us 220, which is the number of correctly classified examples. Then 220 divided by 240 gives us 91.6. Oh, so we're actually off by 1. That's interesting. Okay. So maybe 0.5 isn't our classification threshold. Let me look this up. TensorFlow classification threshold. And we use binary cross entropy, right? This one. Does it say? It's interesting. I'm not sure. I'm actually not sure. Does TF use 0.5 as classification threshold? There is not any threshold involved here. Oh, right, it just takes the maximum. Oh, right, okay, okay. Very good. So we won't do 0.5, we'll just take the max of the wait, but that, give me 1 second, I'll be right back. Alright, sorry guys, I figured out the problem. It's a very stupid problem. I was summing over the predictions, which is not actually the correct predictions. I was literally just seeing what percentage was legendary Pokemon, right? So because if I do greater than 0.5, if I make this a numpy integer, whoops, sorry. You can see this isn't a 1 if we got prediction right, 0 if we got a prediction wrong. This is 1 if the Pokemon is legendary, right? Rather, if the model thought the Pokemon was legendary. It doesn't say anything about how correct this is. So what I should have done is compare it to y-test. Now, before I do that, I'm going to have to actually I'm going to have to stack this. So you see these are all individual arrays in there. If we use numpy.stack, specify axis 1, I believe. Not yeah, axis 1. This stacks it all into one thing, right? Just want to make sure it's the right axis. Yeah, this is not 2. No, it's axis 1. Okay. So now we have a proper array. Now we can compare it to y-test. Test y-test. Why doesn't this work? Oh, interesting. Okay, we'll use hstack then. Don't specify axis. So this one is actually just a single bracket. There were 2 before. So not equal to y-test, and hstack stands for horizontal stack. Alright, now we have our actual, like, true if we got it right, false if we got it wrong, right? We're comparing it now to the true results. And so we turn this into ints. Now we can use this. We'll call this predictions. Will be this. Okay. Now, yeah, let me just keep that on the screen. What we're going to do is we're going to get the indices of all the places where we got an incorrect prediction, right? So that's the ones, right? So 1 here actually means incorrect because I would not equal to. So we could check how many did we get wrong actually. So this is what I was trying to do before, but I was summing over the wrong array. Oh, predictions. 11. So if we do 11 divided by 240, which is the total length of a y, right? So length of y-test is 240, so 11 divided by 240. This is the percentage that we got wrong. So if we do 1 minus that, we get percentage that we got right, which is 95.4%, and that is the same as our accuracy metric. So I should also note that this should actually be greater than or equal to. It wouldn't change the actual results, they're still the same, but technically if we had 0.5 it would be classified positive. So then what are we doing? Okay, let us get the indices for the mislabeled examples. So to do that, alright, I'm going to get the indices of this. So indices of predictions. To do that, we just do .index. So the thing, sorry, not predictions. We're going to do y-test sub-predictions. Oh, this should actually, okay, so we don't cast this to int. We're going to keep it as true false. And so we have true false. Then we can index at an array of booleans to get only the ones. So now the indices we have here are only the ones in which we had true. So 696 is in there, 667 is not, right? So with this, we can now get the index. And that's going to give the list of all the indices that we misclassified. So let's call that mislabeled indices. Okay. Now what we're going to do is check, okay, in our original data. So remember we saved data.raw? This is why I did this. We're going to get the examples in data raw, but only the ones that we misclassified. And all columns. So these are the actual Pokemon that we misclassified. And what I want to do now is see what kind of Pokemon are these. And I don't mean like what type are they. I mean in terms of the other Pokemon, what makes these Pokemon specifically difficult to classify? So for that, we're going to use PCA, Principal Component Analysis. If you don't know what PCA is, it's this amazing technique, unsupervised learning, that allows us to sort of get the principal components, is what they're called, the directions in which the data is most variant, or most spread out. And then we can graph all the data in terms of the principal components rather than in terms of the features. So if we try to graph well, how many features is this? Our original X shape, right, there's 26 features. We would have to do a 26-dimensional graph, which is impossible. So what we can do is find upon which two axes in 26-dimensional space does the data vary the most, and then take only those two axes and plot on that two-dimensional graph. And we get most of the data retained, most of the variance on the original data is retained because the principal components are arranged in such a way that the first two carry the most variance. And I'll just show you what I mean if you're not following. We'll create a new PCA object, which we get this PCA from sklearn, and encomponents 2. So that means we're going to take 26-dimensional feature data and compress it down to 2 dimensions. Basically by so a principal component is sort of like an amalgamation of other features. You can think of it that way. So we're taking the two most important ones. Sort of like a change of basis also, if you know linear algebra. But I'm going to make a new data frame. It's called data reduced. That will be okay, it's going to be a new data frame. I'm actually just going to save that pca.fit_transform data. So this is going to do exactly what I said. The math behind it's a little involved, but basically it's going to take these 26 features that we created, and this includes the one hot features, right? So you can't see them all here, and it's going to sort of change the perspective of how we look at them. So if you could imagine, you can't really imagine, but all that feature data is encoded in 26-dimensional space. There's two directions in which it varies the most. So you could think of like an ellipsoid or in an egg shape. You can see that there's an infinite number of directions in 3 space, but there are two directions in which it varies the most, which is the major axis and the minor axis of the ellipsoid. So it's basically going to change the way we look at it. So it's going to shift away from the feature coordinate system into this new principal component coordinate system, and it's just going to take the two most important ones and reduce it down to that. So we look at that now. I might make a video on PCA. It's very interesting. This is now okay. So this is why I wanted to turn to a data frame. So I'm going to make a data frame, and I'm going to keep the columns. I'm going to name the columns PC1 for principal component 1 and PC2 for principal component 2. Alright, so now we have this new data frame. It has just as many examples as before, but now it has 800 examples. Sorry, 2 columns. Right, it already had 800 examples before, but now it has 2 columns as opposed to 26. So let me graph this, because now we can graph it. And we still get a pretty good sense of how the data is distributed in relation to itself from just these two, because most of the variance of the original data is retained in these columns. So sorry if that was a long explanation. I'm going to plot a scatter plot of these. Alright, so plot.figure, we'll give it a fig size of let's do 20 by 10. And scatter. So this is a scatter plot. On the x-axis, we're going to plot PC1, and on the y-axis, we're going to plot PC2. So data reduced sub PC1, and on the y is data reduced sub PC2. And plot.show. Alright, so this is what I'm talking about. So this was originally in 26-dimensional space, but it got squashed down to 2 dimensions, and now we can see them. We can see the data in 2 dimensions, and along the x-axis, this is our principal component 1. This was the axis upon which it was most varied, so most spread out. So you can think of this as sort of like being a hidden feature as a combination of the other features. And then the y-axis is the second most variant direction in 26-dimensional space. So now what we should do is let's try to get a better sense of what this data is. Because right now we don't know what this represents at all. Okay, we don't know what PC1 represents. We don't know what PC2 represents. And I think let me just actually give this some labels. So plot.x label PC1, plot.y label PC2. Okay, and then plot.title PCA plot, scatter plot. Alright, so let's make it light gray. So see color equals light gray. And then I want to see which of these are legendary. Okay. Or actually what might be better first is to see which of these did I misclassify. So I already have this mislabeled indices, right? So what we could do is color the ones that we mislabeled differently than the others. So I'm going to put another scatter plot overlaid on top of this one. And this one will be data reduced, but I'm going to only locate the indices that are mislabeled. That's what we had from before, and we still want all columns, right? Actually, no, we only want PC1, and we'll do the very same thing for the y-axis, but with PC2. Alright, and let's give that one a color of, I had a good one here, let's see, orchid. Let's use orchid. And I accidentally put a parenthesis here, okay. Alright, so now we can see, out of all the data, there are a few of them that we mislabeled. Not too many, right? I think 11 was the total number. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 11. There's another one right there. So, what can we do next? Well, this is very interesting to start because we can see that it seems like examples with a very high value of PC1 are the ones we misclassified. We didn't misclassify any of the ones down here. And we also notice that the shape of the data changes a little. Here it's much more clustered together around a single mean. Here it's spread out, almost stratified into these strips, right? So there's some sort of shift that happens here, right? Between this right here, this line in PC1. So PC1 of about 100, 130 or something. There's something happens. And let's see if we can get a better sense of what that is by checking where are the legendary Pokemon in here. So I'm going to plot 2 more scatter plots on top of this. I'm going to plot all the ones that are legendary, and then I'm going to plot all the ones that are legendary and were misclassified. So before that happens, I need to make legendary indices. And so we're going to do data. What data looks like is our numerical feature data, right? That still has our legendary column encoded as a 0 or a 1. So data.query will allow us to get only the rows in which a certain value is, in which a certain condition is met. So we're going to query with the condition legendary equals 1. And now that will be all the ones, but only the ones where legendary is 1. From that we can get the index, and now we'll have the indices for our legendary Pokemon. Legendary indices. So in addition to that, I want to get the indices where we have a legendary Pokemon that was also mislabeled. And so for that, I'm going to use numpy.intersect1d, which will just the intersect of the two index lists, and we're going to intersect mislabeled indices and legendary indices. Pretty straightforward. And then so we're going to store that in long name, I know, but mislabeled legendary indices. Alright, and now we can create these 2 new ones. One I'm going to put between the two. This will be the legendaries. It's because I still want the misclassified ones overlaid on top, right? So this will be similar to this thing, except instead of mislabeled indices, we're doing legendary indices. And the color here, I'm going to make dim gray. So, I don't know if I should show it yet. I'm just going to do the other one too. Well, actually, I'll just show it. Alright, so, very interesting, right? We can see that, so the light gray, here, let me include a legend. And, for the sake of time, I'm just going to copy and paste this legend I had. Like this. Okay. So, non-legendary is light gray. Legendary is this dark, almost black color. And the not, well, this is actually all misclassified. It's because I have this other one. You know what? Why don't I'll just paste it in. How do I do this one? Oh, right. Okay. So it's the same thing, except instead of doing mislabeled indices, we're doing mislabeled legendary indices, which was the intersection of the two. Mislabeled legendary indices. And the color here we can make, I found a nice one, medium spring green. Alright, so this is the full picture. You can see up here, the light gray is non-legendary Pokemon that were classified correctly. Legendary, the dark gray here is legendary Pokemon that were classified correctly. The fuchsia color, or the orchid, is non-legendary Pokemon that were misclassified, and this light green here is legendary Pokemon that were misclassified. So what's so interesting about this is that all of the legendary Pokemon occur past that point that we were talking about. See, when the data shifts, that's when the legendary Pokemon start to appear. And so our model figured that out, and that's why we see nothing misclassified here, because it knows if we have so we could think of PC1 as sort of measuring the strength of a Pokemon. That's one way of looking at it, because we could consider strength. I don't know. It's a combination of these, right? When these are all high, you could think of. I don't know if that's exactly what it's seeing, but there's some relationship it sees that when they take on certain values, we start to get legendaries, and if they're under certain values, we just don't have any. So this is mainly why we have such a high prediction accuracy and AUC. But over here, we start to get, it's not as easy to tell, right? Because they're all sort of in these strata, and you can see the legendary misclassified. It had a hard time realizing these were legendary. Even though, right, if I turned off the colors, we would have a hard time also. Non-legendary misclassified, like things over here, it's not sure what to do with them because the rules are a little different. And this is a bit of a simplistic way of looking at it, but it still gives us a better sense of what the model is doing. And I think if you want a greater sense of how the model's performing after training, I think PCA is a fantastic way of getting that insight. And so I think that concludes today's video. I hope you liked it. If you did, make sure to subscribe and hit the bell and leave any comments in the section below. I'll see you all tomorrow. Have a fantastic day.